from journalistic, and I will present I will show that we have a theory to cover all existing covariance inflation methods. So first, I will not talk about the adaptive inflation or perturbative physics, but I will talk about the covariance inflation methods that we apply at data assimilation cycle and to increase the ensemble spreads. So up to now, we know that we have 4 methods. So we have a prior multiplicative inflation. We inflate the background error covariance by this. And another one, this is we inflate a background. We inflate the analysis error covariance. And we have RTPP and RTPS. And we usually think that is an ad hoc method because the nature of this method is not so clear. And I hope that after this talk, you will know more than 10 other covariance inflation methods. So there is some questions that when I do this study. So that's because we know that if we inflate for the posterior inflation methods, we only inflate BA, but it's somehow similar to we inflate background error covariance. But the posterior covariance inflation methods cannot show how we inflate the PP, but they only say that we inflate BA. So that means in this case you inflate the perturbation only, but you don't inflate the analysis increment. So this is inconsistent. We use different background error covariance for analysis perturbation and analysis increment. And another that how can we explain the relaxation form of RTP and RTPS and another other methods. That's if we have any other posterior CM methods or not, and do they have a relaxation form or not? So another problem, that's the RTPP versus RTPS. That's we know that they have the same relaxation form, and we think that the perturbation should behave similar. But actually, it's different because usually we see that RTPS tend to generate analysis perturbation that's with small spread, smaller than the RTPP, and no one knows why this behavior. And we want to show that the theory can explain this behavior. So first, I have some background. So I will show the decomposition form of data assimilation. So I think that you already know this equation. So this is for analysis, and this is for analysis error covariance. So, and if we assume that we have some decomposition form of BP, we can rewrite this as this one. So I will go through this one, and then we apply this the square root, the inverse square root of R to this one, and after that, we perform singular value decomposition SVD for this perturbation in observation space. This is the scale perturbation in observation space, and we finally we have this one. I will not go into the detail because I don't have time. So this is these is the innovation vectors, and we decompose it in the EU basis, and after assimilation we have this form, and this one is background perturbations, and after analysis after data assimilation we have this form, and this is the background error covariance, and after the data assimilation we have this form. So you see that it's very clear that we have some scaling factor here, from here to here and from here to here. So that means we have this makes sense because if we assume that we have observation everywhere and we only have one kind of observation, and that means actually it's come back to the we have decompose this into the data assimilation problem for X modes. So that's actually we have a one-dimensional DA. It's a very well-known problem. So that means we know if we know the decomposition form of data assimilation, that means we know that we have I will call the perturbation response function. That's if we do not perform the data assimilation, we have this one. But if we have data assimilation, we obtain this form. So we have this function. just because we have data assimilations. So we have, this is order preserving of this of the singular value here, from here to here. So now I will say about the inflation. So the first I must say that's I have something to say about the ensemble transform matrix. So if we this is in modern space, we have this one. But if we take the transpose, we have this one. And actually, this shows the ensemble transform matrix in ensemble space. Actually, the meaning is very simple. That's it. You take x perturbation and you project to x most VIs. Then after data assimilation, actually you multiply this with the lambda. And this one is the eigenvalues of this matrix. So the idea is that instead of lambda, now we replace with the f lambda, and we replace the analysis increment with the inflated analysis increment. That's if we replace lambda here by f lambda, and this one we also replace the lambda by f lambda. This for the perturbations. But not any function that can be inflation function. We need 3 conditions. So this is a definition. We need so if we have any spectrum here of ensemble transform, we will associate it with a coordinate function. That's we will call the inflation function. So this need to follow 3 conditions. That's the functional condition. That's it should increase almost, and the no observation condition. That's if we have a no observation, the analysis perturbation should be the same as the background perturbation. And the order preserving, that means the response function should be an increasing function. So we should preserve the order of singular values. So the first one, this is the idea. That's if we change from here to here. So that means we want this one should be greater than this one for all most. So that means we should have this one greater than this one. And we extend this for the whole interval 0, 1. So we require that is greater than lambda. The next one is no observation condition. That means we should have this one convert to 1 whenever O lambda converts to 1. And the last one is the order preserving condition. So I will show here an example. This is a two trivial example. So we have if we have performed no assimilation, we have this one equal 1. If we have no inflation, this is equal lambda. But if we have a multiplicative inflation, we have this function. And if we have a posterior multiplicative inflation, we have another function. I will not go into the detail how we derive this function, but it's easy to derive. So this is an example of so here we have this one is a no assimilation, some inflation function. So this is inflation function. So we have a no assimilation. This one is this is a no assimilation. This one no inflation. And if we perform prior multiplicative, we have this function. And if we perform the posterior multiplicative inflation, we have this function. So this is a perturbation response. So this one is no assimilation and no inflation. And if we perform the prior multiplicative inflation here, and this is a posterior multiplicative inflation. So this shows up for the first time. We see that's the first time that it's very clear that's and posterior multiplicative inflation. That's 2 different methods. It's not the same. If we keep the same row, this is actually the row. We have 2 different methods. Okay, so now this is some summary of the theory. And I will skip another very interesting theory. That is the prior inflation. We inflate the singular value instead of the eigenvalue, but I don't have time, so I will skip this. So this is the flow chart of the theory. That is we have a perturbation here. We perform the SVD, and first we perform data assimilation. Then we have this one, and then we inflate this lambda to f lambda. But we can go another direction. That's first we inflate the gamma, then we perform data assimilation, and we have the same thing. You can have the same thing. And in Venison, it's also easy because I write everything in the observation space. But if we come back to the modern space, it's easy to implement. So this here and this here, it's very easy. That means we only need to project the ensemble perturbation into x vi mode, then we multiply with this one. That's all. So So this is the most interesting part. So the first one is a linear inflation function. So if we assume that we have a f lambda equal I lambda plus b, then we can have this one. X inflation equals a x and analysis and plus b and multiply is the background perturbations. So if we apply the functional and order resolving condition, we have two constraints here, and the problem is that the first one I saw with the constant inflation function, that's the f lambda equal b. So if we fix this b, that means the no observation condition means that the f1 should be 1, that means b should be 1. So that means if we need to, if we want to obtain the non-trivial solution, we need to parameterize b. And here, so I saw that we can parameterize b by some form here. That means we can use the trace of t and all the determinant or any spectrum norm or forward norms of t. Anyone can possible. But we can also use this somehow mimic the norm of the ensemble transform matrix. Then after that, we have this form for f lambda if we apply the no observation condition. So do you know what is actually this is so that we have a diagonal ETKF. That means we have this inflation is proportional to the background perturbation. So the next, so this is the big picture for constant inflation function. This one, and this is response function, and this is the inflation function. So next one, the multiplicative inflation function. That's if we apply this f lambda equal a lambda, and if we choose this one to parameterize a, we will have a f lambda equal a lambda. This one, and we, if after some mathematical operation, you will see that we have this one. And can you guess what it is? Actually, this is RTP, we recover RTPS. So we recover from here to here by the linear functions. And so here's some form, some inflation form for the RTPS. So we have, actually we apply this linear functions, and we have this perturbation response. But we have a more surprising issue. RTPS is not a unique relation of multiplicative inflation. If we, instead of delta x, the norm of delta x divided by delta x, if we choose the mean of lambda, or if we take the inverse of one, it still works also. I show here the example for the Lorentz 40 variables experiment. So we have the red line, the RTPS, but if we choose other form of parameterization, we can still obtain the minimum of IMSE. This is IMSE, and this is a ratio to check the dispersive of the ensemble from this experiment. So I use the ETKF for this problem. So this is the check. I check with the RIKEN observations. So and this is the blue line here from the RTPS, and other one is I use the other form of the parameterization, and it also works well for RIKEN observation experiment. So the next one is the fixed line here. That if we fix A and B, what we're going to say that we should have this form. And can you guess? Actually, this is a RTPP. So we have this is some function form of RTPP, and this is a response perturbation. And if we so that's this is one for RTPS, and this one RTPP. So it's so clearly that we have two different methods here, because the RTPP tend to increase. We have a no bound for RTPP, but in RTPS we have a bound here. So this is another, but I don't have time, so I skip. We have another method here. So another quadratic. But now if we change this to quadratic function, we will have this form. So, but we have problem. That's we have a XA here. So we think that we should set it to 0. So we only have this one. So we have this form. It's better to apply this one to save the commissioner resources. So we have this one, and after that we have this form, fixed quadratic inflation function. And can you guess what it is? This is a deterministic EnKF, because if we set A to 0.5, we will have this one. So this is actually come from the quadratic inflation function. Okay, so I don't have time. So this is a perturbation response function, and this is an inflation function for quadratic case. So I skip this one. This is for cubics, but we will not go to the cubic. Okay, so that is, I have many other topics, but I don't have time to explain everything. It maybe take 1 hour to 2 hours to explain everything. So this is a summary of so that we have a theory that explain everything, all inflation methods, and for the constant inflation, we show that we have a diagonal ETKF. Another we show RTPP and RTPS. If quadratic, we have something like DETKF. So this is a picture for the. This is a picture that's a summary all existing inflation methods that we know up to now from this theory. Okay, sorry, that's I over the time.